All right, in this video, we're going to look at the trig function values for some special angles. And so this first triangle right here is kind of special. Notice how the two short sides appear to be almost the same length. I intend for them to be the same length. This triangle right here is a 45, 45, 90 degree triangle, okay? And so we're going to be able to look at look at the special relationship that holds true for any 45, 45, 90 degree triangle, okay? So a lot of times we call it that, a 45, 45, 90 degree triangle. All right, and then over here, another special triangle we use quite a bit is one that's called a 30, 60, 90. If this angle's 30, we know this one has to be 60 since there's 180 degrees in your triangle. So this is a 30, 60, 90 degree triangle, okay? And so since trig functions are really ratios of the lengths of the sides, and they depend only on the size of the angle, not the size of the triangle, we can kind of arbitrarily call this side length 1. But then there's a relationship that holds true. If 1 is the length of the side opposite the 45 degree angle, then this side also has to be 1 because it's opposite a 45 degree angle. So they would have to have the same length. And then the Pythagorean theorem could be used to find the hypotenuse of the triangle. So we could go in and do, all right, let's see, 1 squared plus 1 squared would equal this side over here squared, so that the hypotenuse squared. So x squared would equal 2. So x would equal positive or negative square root of 2, and it's a length of a triangle, so it's only the positive one. So that would be square root of 2. And so the ratios of the sides of a 45, 45, 90 degree triangle are always in the ratio of 1, 1, square root of 2. Okay? The lengths of the sides could be bigger, like it could be 5, 5, 5 square root of 2. But that's the ratio of the sides, 1, 1, square root of 2. Okay, so let's do a similar analysis to figure out what the ratio of the sides in a 30, 60, 90 would be. First, I want you to imagine making an exact copy of that other triangle and just flipping it down here, where this would also be 60. Then this would be 30. All right, and I'm doing that because then that makes this big triangle here, this one, makes it equilateral, so it have a special relationship. So if I designate this short side right here as having length 1, then we know this is an exact copy, so it would be length 1. But then that means that this would be length 2. And that's a side in this blue triangle, a side in an equilateral triangle. So if that side's 2, so is this one, so is this one, okay? All right, now we really don't care about the big triangle. We care about the 30, 60, 90 triangle. So we have one thing left to find, and that's the length of this piece right here. And so we're going to use the Pythagorean theorem again to do that. So we're going to go in and we're going to take the 1, let's see if I can squeeze it in over here. We're going to take the 1 squared plus the x squared, and that's going to equal the 2 squared. So x squared is going to equal 4 minus 1, which is 3. So it equals positive or negative square root of 3, but then it's the length of a triangle, so it'll be the positive one, positive square root of 3. Okay? So when you've got a 30, 60, 90 triangle, okay, so that's just this guy right here, the one in green, the ratio of the sides are going to be 1 square root of 3 and 2. Okay? 1 square root of 3 and 2. Now really, when I remember this, what I do is I tell myself the ratios of the sides of this triangle would be 1, 2, square root of 3. It's just easier to say it that way. And then I know this has to be the shortest. This has to be the longest. And so then I know this goes opposite the 30 degrees, this goes opposite the 90 degrees, and then that leaves this for the 60 degree, okay? All right, so you need to know how to figure them out, or you need to know what the simplified ratios turn out to be. And so let's go over here then and think about that. Now that we know the ratios of the sides and we can see their location, when we do the sine of 45, it's just going to be 1 over square root of 2. But then you have to rationalize that. And you'll hear this quite a bit. So that's square root of 2 over 2. Well, cosine is going to turn out the same way because it's also 1 over the square root of 2. Doesn't matter which angle you focus on. Okay, you're going to have the sine being 1 over the square root of 2 and the cosine being 1 over the square root of 2. So we can just go ahead and say that. Okay, square root of 2 over 2. All right, now for tangent is, if we're focused on that angle, it's opposite over adjacent. So that's just going to be equal to 1. Okay. All right, now over on the 30, 60, 90 triangle, the sine of 30 would be 1 over 2. 1 over 2. Okay. The cosine of 30 would be the adjacent side. That's the longer one. That's the square root of 3 over 2. And then for tangent, you have to do opposite over adjacent. So you have to make sure you're focused on that 30-degree angle. You'd get 1 over the square root of 3, but then you'd have to rationalize that one. And so it would become square root of 3 over square root of 9, which is just 3. So square root of 3 over 3. All right, now, when you do sine of 60, sine of 60 has to look at the side opposite the 60-degree angle now. So you have to change your focus to this angle over here now. And so the opposite side would be square root of 3 over the hypotenuse of 2. When you do cosine of 60, that's the one that gives you 1/2, because you have to do adjacent over hypotenuse. So the adjacent side over the hypotenuse. And it's not a coincidence. See how the sine of 30 and the cosine of 60 turn out to be the same thing? That's always true when you have angles like this that are complements of one another. The sine of one of them is going to equal the cosine of the other. Okay. And then when you do tangent of 60, probably the best thing to do is to go back to here, or just look at the triangle again and see how you're going to have opposite square root of 3 over the adjacent, which is 1. So it'll be square root of 3 when you're finished. Okay. All right, now what you need to memorize are the ratios of the sides. And then you can figure out the sine, cosine, and tangent again. So I think it works best just to know 1 square root of 2, and then I do it this way, 1, 2 square root of 3. And make sure you can put them on the triangle in the correct way. All right. And they wind up using 30, 60, 45-degree angles quite a bit. And these are some that you're going to be expected to do without making use of your calculator. Okay. All right. On this same video, let's go ahead also and just state something officially that I said earlier. Here we're looking at some of the fundamental identities that hold true for these trig functions. And one of the things that we've already commented on is that sine and cosecant are related. They're reciprocals of one another. And so typically you want to kind of understand what cosecant is. And so a lot of times the way you think about it is you say, well, it's just the reciprocal of sine, 1 over sine. And secant, well, that's just the reciprocal of cosine. Make sure if it's an S that you use the one that's different, okay? That has a different first letter, okay? All right, and then cotangent is just the reciprocal of tangent. You know how tangent was opposite over adjacent, and then cotangent was adjacent over opposite? They're just reciprocals of one another. Well, the same holds true for this, even though you don't go in this direction very often. Sine could be thought of as 1 over cosecant of theta. And you should never just write cosecant. I know it's tempting, but I really want you to think about it in terms of function notation. So cosecant by itself really doesn't have any meaning. It's function of some angle in this case. Okay, and this would be 1 over secant, and this would be 1 over cotangent. Okay. All right, and then one other thing, there are some quotient identities that define tangent and cotangent in terms of sines and cosines. And it turns out that tangent theta always equals sine theta divided by cosine theta. And then since cotangent is just the reciprocal of tangent, you can flip that around and say cosine theta over sine theta, okay? And you can see how that would be true, okay? If you think about sine theta, think about why that's the case. Just look at it for a minute. If you had tangent theta equaling sine theta on top, and sine is opposite over hypotenuse, and there's my big fraction bar, and cosine is the adjacent side over the hypotenuse, okay? You see how that would work out? We multiplied the top and the bottom by h, we could cancel out the denominator, and we'd wind up with O over A. So tangent can be defined in terms of sine and cosine if we needed to or wanted to, okay? And that kind of proves it over there. All right, so here's one way we can use that. So let's look at this question. On this question here, we don't know the angle, and we're not expected to find the angle. It just says we know the sine of some angle, we know the cosine of some angle, and you're supposed to use these identities to figure out the value of the other trig functions. So let's think about sine, we already know, and cosine, we already know. Well, because of what we just said, we can get tangent then, because tangent is going to equal the sine divided by the cosine. And then this is a complex fraction when you have a little fraction inside of a bigger one, so you have to simplify that. And the easiest way, in my opinion, is just to look at the little denominators and multiply the top and the bottom of the fraction by the same thing. And then we can see that tangent theta would be 2 over square root of 5, but we can't leave it that way. So we go in and we rationalize the top and the bottom, and we wind up with 2 square root of 5 divided by 5, okay? So tangent theta equals 2 square root of 5 over 5. All right, now once you get those three, you can get the ones that are related to these by just using the idea of a reciprocal. So like sine and cosecant are reciprocals on one another. So cosecant should be 3 over 2, okay? Cosine and secant are related to one another. So this should be 3 over the square root of 5, which we have to rationalize. Okay, so that's going to be 3 square root of 5 over 5. And then cotangent of theta is just going to be the reciprocal of tangent. And probably the easiest thing to do is to look right here and flip it over. Before you rationalized it, look at the 2 over square root of 5, and then you can see when we flip it, it's already simplified and good to go. Okay, so we never knew what the angle was, but we could use the quotient identities and the reciprocal identities to figure out the value of the other trig functions. Okay.